Hello again, everybody, and welcome to another Geo-Institute live stream. This is the final live stream in our GI Summer of Live. We'll tell you a little bit more about some of the stuff that we did over the summer later so that you can go back and check it out if you are so inclined. My name is Brad Keeler. I'm the director of the Geo-Institute, and we are thrilled to have you with us for the 2024 Monismith Lecture on Pavement Engineering. If you don't know anything about the Geo-Institute, well, we are a technical society with about 12,000 members, most of whom are geotechnical engineers and/or geologists, and we are part of the American Society of Civil Engineers. And if you like what you see today, and I think you're going to, we're bringing you the best, you should click like, subscribe, and get notifications, and we'll let you know every time we post something to the YouTube channel. A couple of public service announcements for you today. It is, as you know, back to school time. And what better time than to make a contribution to Geo-Institute student programs? You can do this while you're at geoinstitute.org by clicking on the tab at the top that says Student Participation Fund. If you do that, you'll be given all kinds of instructions on how you can donate to the Student Participation Fund. 100% of your contributions are tax deductible and 100% go to students. We're all out of Carl Terzaghi bobbleheads now, but we will have Ralph Peck ones coming soon. So you want to keep your eyes out for those and have a little something to put on your shelf after you make the donation. Now, about the proceedings today. I mentioned that this is the Carl L. Monismith Lecture. The Geo-Institute awards this every year since 2010 to a deserving member who has performed exceptional feats, I guess we'll call it that, in pavement engineering. This year's winner is from the University of Texas-El Paso. It's Soheil Nazarian. And here to tell you a little bit more about Soheil and a little bit more about the award, and maybe a little bit about himself too, from the GI Board of Governors from Texas A&M University is Anand Pupala. Anand, welcome and thank you for running the show today.
Thank you, Brad. It's a very tough job to follow our greatest communicator, Brad Keeler, but I'll do my best. Again, I thank you for this wonderful opportunity at the Board of Governors. I'm here to present 2024 Carl Monismith Lecture by Professor Soheil Nazarian. His lecture is titled Extending Mechanistic Design Principles into Construction and Maintenance of Long-Lasting Pavements. As you all know, the ASCE Geo-Institute has established this lecture in recognition of Professor Carl Monismith's contributions to pavement engineering. Professor Monismith's teaching and research career at UC Berkeley in this pavement field spanned more than 50 years. Throughout this period, he has mentored several graduate students who have disseminated advances in pavement technology all over the world. This lecture is always awarded annually to an outstanding research contributions to pavement engineering. And you can see on the screen the ways you can nominate a very well-deserving candidate for this award process. Highly recommend you to go to the ASCE website, look for this Carl Monismith, and please nominate a deserving candidate. With that, now let me go back to introduce my good friend, Professor Soheil Nazarian. Professor Nazarian is the McIntosh Murchison Chair Professor of Civil Engineering at the University of Texas at El Paso. He has spent more than 40 years of experience in materials, testing, and design of transportation infrastructure systems. He has significantly contributed to the body of knowledge in construction, quality management, and mechanistic characterization of earthwork and pavements using innovative technologies such as intelligent compaction. He has been one of the pioneers in developing SASW non-destructive method and implementation of several other non-destructive testings for infrastructure condition assessment. I had a great pleasure working with Soheil on many projects for different agencies, including Texas DOTA and NCHRP on various different works. It was a great pleasure to work with him all the time. He has been a PI or co-PI of more than 120 plus research projects funded by many federal and state agencies. He also authored more than 300 plus technical articles in journals and conference proceedings, primarily sponsored by the ASCE and also Transportation Research Board. He also received a very distinguished Proctor Lecture Award from International Society of Soil Mechanics and Geotechnical Engineering, and he delivered the talk in Sydney in 2022. And Dr. Nazarian also served in many, many societies, including is the past chair of the Geo-Institute's Geophysical Engineering Committee, is current chair of Geology and Geotechnical Engineering section of the Transportation Research Board, and is also on the executive board of the International Society of Intelligent Construction. I think if you all know it, Soheil, one of the great pleasures you get is Soheil's slapstick humor is wonderful. He is really like, I really enjoy working with him. He's a great friend. And again, it's a big honor. And with that introduction, I would like to request Professor Nazarian to give his talk. Over to you, Dr. Nazarian.
Thank you so much, Anna. Thank you for the wonderful introduction. You know, it's always a pleasure to work with you. And good afternoon to all of you over there. And I'm trying to share my screen. Hopefully I shared the right screen. I have, let's just 1 second. Okay, I hope everybody can see and can see the presentation. Is it in the presentation mode? Everybody can see?
Looks great.
We can see.
Yeah, sure, no problem. Yeah, I am just at awe with having my name and Professor Monismith, you know, one of the mentors of all of us on the same page. So I would like to thank the ASCE for giving me this honor, and I appreciate it. Thank you so much. I just want to start talking a little bit about extending mechanistic design into the life cycle of the pavement. We have been doing a lot of work in the design, but I would like to see if we can get it to the next step. So a little bit of background about me so that you know if I misspeak something because of my education. You know, I have only one class in pavements. It was 1975. And what you see was a bootleg version of the principles of pavement design that fresh at that time by Yoder and Witzak just came out. And we have half of the semester dedicated to that. So that's the extent of pavement that I've had in my career. The rest of it I learned from you guys and from the curiosity and so on and so forth. So if I say things that don't make sense, because that's the reason. So what I learned from that class that I had in 1975 was that, you know, essentially there is a life cycle. You start from planning to design, construction, maintenance, and eventual reconstruction. And then the goal is that to ensure pavement lasts for a predefined life. It's not forever, it's just whatever we want it to be and whatever we are willing to do it. So let's start from there. And in that time, in 1970s, that when in 1972, I started college in 1973. That's when the actual pavement design came out, the empirical ones. And since then, you know, there were revisions, and now we are lucky enough to have the pavement ME, and basically it's quite an achievement. And I guess Professor Witzak that I started with had a big hand in developing this. I started with the slide rule. I don't know anybody is in the room still alive that uses slide rule during their education, but you know that's when that HPE that you see over there came to market, and that's the first one. And now we are access to the supercomputer over here in the Austin, and then we edge computing and the computation, it's out of the roof. You can do anything you want. In terms of the lab testing, we have gone from a Marshall pills and stability to a bunch of sophisticated fundamental and index tests. Construction tools, they have come a long, long way. Now we have all computer control, we have autonomous, and a lot of improvements to get a better quality construction. And of course, the last one is the testing, non-destructive testing. I old enough to use Benkelman beam. It was fun, but you know, you don't want to do it for forever. And then I don't know why it changes my slide. And now we have traffic speed deflection devices that they can just go 60 miles an hour and collect the data for you. So everything has improved significantly. But one thing that has not changed is the way we are dealing with the construction and maintenance and rehabilitation. So there is a mismatch between these three areas. We design based on modulus. We construct based on density. And then we just basically look at the distress and roughness for decisions for maintenance and rehabilitation. So let's look at the goal one more time. And I just took the one that I learned from Yoder and Witzak and changed it a little bit. I want to ensure in a practical manner that the pavement lasts for a predefined life, but uniformly. So there are two items that I'm going to talk, and it's hard for the faculty, but I do. One is practicality, the other one is uniformity. So we want a smooth road, stiff enough, uniform enough, and durable. So this is the ideal steps that we can do it, and then let's look at it, and we can then relax some of it. We want to select the appropriate design algorithm. There are different level, different sophistication of algorithm. We need to choose the right one for us. We need to select the suitable materials for durability. I'm going to comment on that. Durability is important, but it doesn't come in the design. We need to measure the input parameters that are compatible with the design algorithms. Sometimes we just keep using the default and not knowing the property. We want a quality management program that targets with target values that, you know, we can make sure that we have measuring all the parameters that are important and we are monitoring it. Process control, we need process control to maximize uniformity. And then we need an acceptance process based on the stiffness because we are designing based on it, stiffness. And finally, the monitoring the final product. One thing that I love to see as a person who all his life has been doing non-destructive testing, to have a test before you open it to the traffic, because detecting changes is much easier than looking at absolute numbers and making decisions. So that was the ideal. I'm not naive. We have institutional issues. First of all, is a manpower limitation. Everybody knows that that issues comes up. Budget limitations, we're always doing it. And one thing I want to bring it to your attention, if you are working for aerospace industry, 85% of the cost is quality control. When we do highway construction, we spend less than 2% for quality control. So we don't want 85%, maybe a little bit more than 2 would be good. And then, of course, risk assessment. What's the risk of a failure in this time if we have a premature failure and the rehabilitation not working? What are the issues with that? And of course, we need a buyout. We need to make sure that the owners know what we're doing, the contractors and all the designers and people who are interested in between. So I just scratched out ideal and I just put a practical process, and hopefully that would work. And what we're trying to do, first of all, we have to understand we want to minimize the life cycle cost and not the construction cost as much as possible. And then there are 4 important parameters that are interrelated. First, important projects, more important projects, more critical projects need more detail. Analytical modeling effort, we have to choose it again in a way that is pragmatic so that we can get the parameters that are in the model. We need laboratory testing to support the parameters that you need for model, and we need the field testing for quality control and monitoring. These has to be balanced, all four of them, to a level to have that life cycle cost. So to summarize it, we are just having the economy as a foundation. I guess this is geotech, I can use that term. And then we are trying to balance uniformity and stiffness in a manner that we get a durable pavement. So these are some of the things that we have to consider. So I would just to be positive, let's scratch the mismatch and start talking to pathway to compatibility. These are my dreams to get there. And let's start with the design. So the first thing, one of the issues that we are very loose in the definition of stress of the modulus. You know, there are different methods, different ways, and different states that, you know, we can get the modulus, and we have to be very careful how we use it. So I'm showing you some of the parameters that are important: state of stress, temperature, moisture, frequency, and on and on. There are parameters that impact your modulus for the same material under the same condition. Now the measurement, it can be linear elastic modulus. It can be seismic linear, gives you the linear elastic modulus. I like that because there is no transfer function between the field and the lab. But nevertheless, if you want a representative, you can either that is representative of chalk or a volumetric deflectometer. You're going to get a different modulus, which is the slope of the blue line. And then when you go to the lab, you're going to get even a different modulus because that will be the slope of the green line. So you see that we have to be careful. And these moduli are interrelated from these, but we have to be careful which ones we are using. I give you two examples over here, one for the concrete, because it's probably the easiest material to test. And we normally run static modulus, TDS, and I'm just work with seismic modulus. I have seismic modulus, and there are a bunch of different mixes over there. You see that the static modulus is 72% of the seismic modulus. So we can replace one with the other one for that purpose. The other one I want to show you is more difficult, is, for instance, granule soils. We run resilient modulus, and we can run seismic modulus, but run before the resilient modulus. You see over here, the relationship between the two is roughly 55% because of the strain and stress condition. But when I'm defining the modulus on the y-axis, you see that for the resilient modulus, I'm just identifying at what confining pressure and at what axial stress. Because if we just start mixing and matching, the data would be random. But at a given state of stress, you can relate them together. So let's look at the design approaches. I would start with the most desirable to the less desirable. The most desirable is a mechanistic. Then mechanistic empirical, catalog design, and then, of course, empirical. Mechanistic, we are not there, and it would be a while before we get there. Mechanistic empirical is essentially practical state of the practice now. Catalog design, we don't do much in the US. The only time that we do the catalog design the hard way is when we do not change the defaults on the design parameters of the program that we are using. And then, of course, empirical is not very fashionable. Very few people are using it. So my focus would be over here on the mechanistic empirical from now on. So what mechanistic empirical and how much sophistication is just depends like the way you buy your car. You know, you don't go always and buy a Porsche if you are not willing to change the tires every 3 months and pay $3,000. So just depending on how much you can afford to get the parameters realistically, you need to decide on that. So let's look at the design parameters. There are 3 general areas. We have traffic, we have environment, and we have the layer properties. These are the 3 input parameters, and then the details around it. And then these three we can have as different level. Usually most programs have level 1, most rigorous. This is, we measure everything that we put into the program. Level 2 is somewhere intermediate, and level 3 is the least rigorous of all of them. And basically what I'm suggesting over here, we have a need to balance the analysis sophistication with how much we are willing to do site investigation to define the site, how easy it is to material source, not design based on a fictitious material, but a material that we know, and how much lab testing we would like you to do. So if you go to level 1, make sure that you measure it all. The other issue that comes is the uncertainty, because the material uncertainty is a significant issue that we have to deal with. And traffic is the most uncertain of all, because they say if you build it, they will come and build a bunch of homes and stores and things like that, factories. Environment, just basically by nature, is variable, and then layer properties, of course, uniformity is something that we need to understand. So you can go deterministic, you can go approximate probabilistic, or you can go rigorous probabilistic. And if we go rigorous, then we are talking about time. I prefer that, but we have to see how we can do that. The next step is the mechanistic empirical design engine that we use. The most sophisticated can go from easy to most sophisticated. Elastostatic is de facto what we usually use. You can go dynamic, you can go nonlinear, you can go viscoelastic, or you can go all out and consider all these parameters. So if you do that, the more you do, the more time you need, the better computational power you need, and you just have to balance it with the material characterization. I would like to talk a little bit about site investigation. This is the thing that we have to consider it, because a lot of the time the problems that we have with the design is that we don't have a good grasp of the section. Traditionally, we go every 1/10 of a mile or every 500 feet and just drill a hole and see what we have, and then we simplify the cross section. I think we need to shy away from that, and something I call the insurance against change orders is just basically start using some of the much simpler rudimentary way of looking at the variability, and drill based on what these tests tell you, and just put them when you when there are anomalies, just put the boreholes closer. When there are uniform, just go further. Two examples, one is GPR, and you don't need sophisticated analysis. You're just looking for the anomalies. And the other one is resistivity. You see this gentleman is just having a string of sensors, and it just basically walks and collects the data to look at anomalies. And if we do based on that, I think we can improve the reliability of the design. Now, I said durability. Durability, the problem is that we cannot design for durability. It's a holistic thing. This is something that comes with the experience. For instance, we know if there are layer mismatches significant between two adjacent layers, you have a problem. Stabilization, we know that it's going to increase the life. Geosynthetics can separate and just basically strengthen so that we can have a longer life. And of course, geomaterials with the right gradation and adequate hardness, that's something that durability. These are the things that are holistic, and we need to consider it before we go to the design. Okay, enough said about the design. Let's go to the next one and start talking about the construction. Construction, we just basically do based on density. I would just like to see if we can go from that to modulus, because we design for modulus. We are the only industry that we don't check what we design for. So instead of traditional QA, QC, I would like to talk about performance management. This is the terminology I stole from John Sigmeyer from Minnesota Department of Transportation. So essentially, we want to check both material quality and workmanship. I think in one of the ASCE reports, they say that 80% of the problems we have is with the workmanship, 20% with material quality. If you look at the QA/QC programs that we usually have, it's usually we check material quality and we pay less attention to the workmanship. So what do I mean by performance management? Let's say you have a typical flexible pavement 3-layer. The first thing I want to introduce is a structural impact factor. That essentially tells you which parameter, which thickness or the modulus of which layer is the one that is most significant for your design. You see, this is if it's a thin pavement and I do the impact chart, you see that the two parameters that are most important are the modulus of base and subgrade. Those are the foundation layers. And with the geotechnical engineers, that's good. The problem is that most of the effort in quality control goes with the AC, even though it's thin, and less in that one that would ensure durability. The other parameter I would like to introduce is material impact. Which parameter in each one of these, is impacting the performance? For instance, if you stabilize it, is it the percentage cement that you have to worry about, or the stiffness or hardness, whatever it is, moisture, whatever it is, and then you do process control based on that. So if you're doing performance management instead of QA/QC, there's a pre-construction, which is part of the design, and basically on that one, you decide on the parameters that are important, the layers are important, and the properties that are important. And then you can get the sampling rate based on the variability that you can tolerate. And this is just basically part of the design, and it's just basically you're doing it based on in an intelligent manner and in a way that is optimized from the beginning. Now, the next step is the during construction, and then basically we would like to control charts and make sure that everything is the important parameters, not all parameters, not the most expensive parameters, but the important parameters are, first of all, are within acceptable limit, and then there are under control. And if the contractor is doing a great job, if the materials are uniform and so on and so forth, hallelujah, we can reduce the sampling process and speed up the construction. And if it's out of spec, we can stop and the first day or second day, wherever it is, and almost real time, just adjust and make sure that we can bring everything in control. I wish I had a day to talk about that. Intelligent construction technology has come a long, long way where we can just go ahead and basically monitor the process and just basically learn from it and improve the construction process to get it more uniform. And I highly encourage, especially the contractors, to look into it for the competitive edge. Why not density and modulus, And this is my favorite one. Those who have listened to me before, they're sick and tired of this figure, This is a experiment we did, and what you see the blue curve. This is the moisture density. This is the Proctor curve. And I have the 4 points, and we usually get the maximum dry density. Now, the exact same specimens, we ran the modulus test on it. And that's what you see from the red curve. If you look at this as a base material, we usually allow ±2% change in moisture content. If you look at the curve from the MDD to this part to the ±2%, you're talking about a 5% change in density. But in the same range, if you look at it, the moduli are just significantly higher, 300% change in the modulus. So it's necessary to get the density, but getting the density not necessarily tells you that you have a acceptable quality material in terms of the modulus. So let's relate design to construction. So if we measure the again best options to the worst option, measuring modulus before structural design of all the layers, utilizing catalog, and that's very pragmatic. You just have the common materials of mixed designs. You use it all the time. Maybe you can catalog it. There are some empirical relationships that relates the index properties to moduli. You can use that, and then the last one is the presumptive design values. I call it default disease. The default values that comes with the design programs, not changing it ever based on where you are and what you have. So if targets are important. So if you are measuring the modulus, you can set the target with confidence and you know what you're going to get. The same thing with the utilization of the catalogs. But when you're getting to estimating based on the indices, first of all, you want to make it a local and define it for yourself, for your materials, and then estimate target using test strips. And if you're using presumpting design values, by all means, just let's go with the density based because we don't have any basis to check for. What equipment? That's another question all the time. And there are NCHRP 10-84 if you want to get curious about it. We tested 6 or 7 different one of them. All of them are interrelated. All of them work together. And I'm just showing you 2 examples. One is a seismic device you can use, and the other one is 2 lightweight deflectometers that you see over here. What we want something to be layer specific, rapid, easy to use, and affordable. These are the parameters that you need to consider and see what's best for you. One thing I caution you, there are 2 standards for ASTM, and they're using the for the same digits. If you have to be careful to specify one or the other because there is a factor of 1.6 difference between the measurements that they do. So that was something interesting that you have to consider. Target values, again, very, very important. If you are going modulus based, you can set up and you decided on the device, you can make it part of your design. MinDOT, mechanistic empirical already spits out what would be the target deflections, for instance, for the lightweight deflectometer that they use. And from then on, you can just monitor it from layer to layer. We like deflection, not modulus, because the technician can look at the deflection. If deflection is higher than a level that you want, then you're good to go. So what would be the modulus-based performance management? We would love to know what material you're going to use when you're designing, not wait till you design and then see what material you want to get. Use the structural design algorithm that you love, you can afford, you can use, and get the parameters easily, and then get your target from that design algorithm. Material properties and run lab testing as we said, and then determine the target modulus, and then perform compaction. We advocate process control and intelligent construction tools for that to get uniformities, and then do the non-destructive testing and see if you are getting the modulus and if you are uniform enough. What I'm showing you over here is a experiment a project that we had with the FAA. I just want to thank Navneet Garg, for including us in this project. And what you see, every circle is one project somewhere in the United States, and this is primarily based on substrate material. And we are using the concept of the PWL to combine the uniformity and stiffness over there. And what I'm showing you over here on the y-axis is the relative density, usually 195%. And on the y-axis is the moisture content, which is the difference between the moisture content in the field and the optimal moisture content divided by optimal moisture content. I call it the poor man's degree of saturation. And the bigger the circle gets, the bigger the variability of the results that you have. What you see over here, all the green ones are the ones that passed with the PWL greater than 80. And then the other one is between 50 and 80. You just have a penalty, but it's accepted, so it's not removed. And you see essentially none of the sites there was anything to be removed. They were just all accepted. Now, there was a modulus measurement with every single one of these projects that you see. Now, this one shows you the PWL you see at version of that. And what we have over here is a little bit different: coefficient of variation of dry density and coefficient of variation of moisture content, and then the PWL circles that you see over there. Red now, it just basically is replaced, it's not acceptable. And you see how many red I have. And you see that the circles, if they are small, it doesn't mean that, uniform, but it doesn't have the stiffness. So this is another indication that we have to do it. One of the concerns that we have, that we do not test as many pairings that we want. We just have a 1 or 2 tests per sublot or something like that, and to accept the material. So there's a big risk for the owner over here. So what we did, we just went and several of the sites that I showed you, we had around 40 points in like 170 meters of the site, for instance, or 150 meters. And we randomly went and selected 4 to 7 samples 10 times and look at the coefficient of variation to look at the uncertainty. And what you see over here, that's a result for 5 different 1, 2, 3, 4, 5, 6 materials, 2 bases, subgrades, lime treated subgrade, and so on and so forth. And what you see, the conclusion is that the larger number of samples, the less uncertainty you have in the result. So the pragmatic one is the 7. And if the 7 is enough, why don't we extrapolate and see if we can get a lot more? And that's where I'm going to talk a little bit about intelligent compaction, because intelligent compaction is giving us a lot more data than the few that we are testing, as is shown over here. So essentially, if you're not familiar with intelligent compaction, it's just a regular roller. We install an accelerometer, either 1-dimensional or 3-dimensional, on the roller to measure the vibration. There is the acquisition display, and then there is a GPS unit over there. So it's a georeference. That vibration of the roller is the input. And based on that, we can just do some judgment on the variability of the material and the stiffness of the material. Just to get you there, this is what FHWA put out in, I believe, 2017-18, and they defined intelligent compaction at 5 different levels. Level 1 and 2 is essentially indices, vibration indices of the roller. Level 5 and 4, they are getting sophisticated analytical combined with the experimental data to get moduli and stiffness. So level 1, 2 is very easy to do, it's implementable, and it just basically collect the data as we go along, compacting, and it's very good for uniformity, it's an index. Now, if you want modulus and stiffness, then you have to go to level 4, 5, which is more involved. So let me give you a little bit of detail. Some of the level 1, 2 are, for instance, Caterpillar uses a parameter called CMV, Palm uses HMV, Sakai uses CCV, and essentially what it is, they look at the vibration frequency and its multiple, and there's different the material, the different and higher the amplitude of the multiple would be, and then based on that, they'll come up with the index related to stiffness. It's relative, but it works well, so it would be good for uniformity. Now, if you want to go mechanistic, there are other ones like just basically get the stress strain curve or the load displacement curve, and then you can interpret, or you can have a more sophisticated spraying dashboard model that you can use it as a forward model, and you just try to back calculate this K2 and C2, which is the soil properties that you have interest. So let's take the low-hanging fruit, and that's level 1, 2 for uniformity and PASCON. PASCON, the process control uniformity, is a parameter that we're trying to understand at this moment. We don't know how uniform we are, and get a handle over it and how we can improve it in real time during the construction. So this is a case study that we do. We talked with a bunch of contractors, a bunch of DOTs, and people who are interested, and we just heard about the concern that they had, and we just came up with this scheme you see over here. And the concept is that as you roll, you're collecting the data, but we came with the concept of sublot instead of just doing kriging and grigging, a more sophisticated one. Because this is transparent, it only gets the machine, the numbers that comes from the machine. Anybody can do their own statistics and they would get the same number, so there's no discrepancies, and so it doesn't get into referee and delay of the project. And essentially what we do, we just assume that the sublots are all the width of the roller, and the length, whatever you want. We use 25 feet, but you should use something that you would be comfortable in asking to be get reworked if it's not uniform or stiff. In this case, we use 25. And this is what you see, the color coded. They are not fancy mesh colors. They're just basically yellow, red, green. From the days that I worked with the Corps of Engineers, I learned that. So whenever it's green, it means that you are above average. These are the coefficient of variation. It means that your coefficient of variation is in control. For us, it's 25%. If it's yellow, it's between 25 and 35%. And when it gets red, it's above 35%. As you see, there are some of them, the coefficient of variation is 72%. So it's depending on where it's too variable. We need to do something about it. It's very, very easy when it's at the subgrade level to go either work and improve this one. And don't worry about it, because any soft layer or in non-uniform layer, we can show you that it would propagate all the way to the surface. Now, if this, that's what we can do. Now, if you want to go to level 4, 5 and estimate modulus and stiffness, that's available too. But this one, like anything that you're back calculating or doing the inverse properly to get the stiffness, it needs a forward model. And the forward model is just essentially you have to model the roller on top of the soil, 1, 2, or 3 layer, whatever you want, and get the responses of the roller to do it. Very time consuming and it's not practical. So how do we make it practical? We just started looking at the artificial intelligence and looking at machine learning. So we are lucky enough to have access to the supercomputer, and for a couple of years we let it go, and we have tens of thousands of cases with different material properties, different nonlinearity, different structure. And based on that, you can generate a neural network to get you an instantaneous response estimate of the value. And this is what you see, the results of the finite element versus, which is the model that we use. Some of them are taking like an hour of the supercomputer to run to what we instantaneously predict with the neural network. I think it's good enough given the variability that we have in the system. Now we can real time get every single data point over there and turn it to the modulus. One thing that we caution you, the model is never perfect. You always need to go to the field and do some local calibration. And this is what we're suggesting for local calibration. Just basically go and roll. And now what we would do, we would just get not the coefficient of variation, but the average of the values that we have from each one of these subplots. And just basically we report it over here. If it's average and above is green, I'm sorry, 75% of average and above is green. If it's between 50 and 70, it's going to go yellow, and then when it's less than that, it's going to get red. So you have to be substantially soft. And basically what we do, we just look at it. If it's soft, maybe we can work out this area and improve it on the right. The rest of it is looking fine. But you need to calibrate it. After you just get this chart, we go to the few places with low, few places with high, and some in between, and run the lightweight deflectometer, and we convert all the numbers with the calibration that you get to the lightweight deflectometer modulus, so that now you have a calibrated value for the modulus. This is the results of all this some of the sites that we have done so far. And the good news, as you see, that on average, we are doing a good job of predicting and the results. The bad news is the error bars that you see over here. That's the standard deviation of the variability that we get with the different devices. You see that the intelligent compaction gives you less uncertainty because we have thousands and thousands of data we average, as opposed to LWD that is limited. So when you look at this one, the uniformity is concerned. We need to reduce this uniformity, and one way of doing it, again, I'm pushing it, I don't talk about it because we don't have time, is intelligent construction technology. There are a lot of nice tools that we can do. Let me go ahead and get to consequences of not doing modulus and going to density. And this is a case study that I love because the contractors are very conscientious, very helpful, and the quality of the final product was extremely good. And the sites were accepted for density, and honestly, it looked very, very nice. So what the design was in the foundation was 12 inches of base over 12 inches of lime-treated subgrade. And these are the design values that they use. The designer used 10 KSI for the lime-treated material and 50 KSI for the base. And right off the bat, if I run the lightweight deflectometer, you see that most places I'm not even close to 10 KSI. And then we went and back calculated the base after we running LWD on top of the base and the subgrade. And you see that the LWD modules are even the red ones are greater than 50 KSI, that they know the lower values are greater than the 50 KSI. So the subgrade was much better. The base was much better, but the subgrade was much less than what the designer has designed for. And this is using the MEPDG, calculating the difference between what they design and what you do. You see that there are some areas that you're 50, 60, 70% underestimating the rutting of the section because of that issue. It's nobody's fault. It's just that we don't compare to see where we are. So let's go to the last one, and that's the compatibility with the maintenance and rehabilitation. And we want to bring the modular somehow into the equation. So what we do right now is functional monitoring. Everybody is familiar with the automated vans for survey. These are amazingly good. They are getting better and better. LiDAR, a lot more sensors, and they give you a lot of information about the functionality. Or you can do it the old-fashioned way, start looking at the cracks and so on and so forth, and measure it. The problem is that when you see the cracks, it's too late. If it's manifest at the surface, maybe it's past the time that is optimal to maintain, and so it's just not desirable. So if you want to get them go mechanistic, we have two tools that we use. The volume deflectometer for the last 40 years is well understood. But the problem is that it's a spot test and it's slow, so we cannot have a lot of data. And in the last 10 years, there is a traffic speed deflection devices that they are coming. There are 3 of them now on the market, and they can collect 200 to 400 miles of data in one day. And they're under intense study right now in the United States and all over the world, just trying to do applications and incorporate it into the pavement design and analysis. So with these, we are hoping that you find the source of the problem before it manifests at the surface and repair it. If you do a good job of construction, of course, we're going to be having to worry about this less, but nevertheless, things happen, and this is a good way of finding it. So what does it do? Just basically, you see the 2 tires, and the red dots you see over here is just basically a bunch of the laser barometers, over here, and basically you measure the ones that is in the United States now at 11 points. And this is the raw data. There's some variability in the data, but nevertheless, you measure every 5 centimeters. What you measure is the red one, is the velocity, and what you want is the black one, which is the deflection with distance. So there are ways of including it. One of the best uses and low-hanging fruit, like the intelligent compaction. The first one is just basically segmentation, so that you can go and see why you have anomalous response in terms of the strength and the structural condition. We can. There are a bunch of indices that are coming and indicators that this is a surrogate for the rigorous analysis, and you can just basically look at those and see what's happening. At the project level, there are some pushes, to start doing what we do with the volumetric pictometer, get the moduli and do back calculation, go remaining life. And of course, for the rigid pavements, it's nicely recently has been retrofitted for low transfer efficiency. So what do we get from this device is something that looks like that. There are 3 negative numbers you see over here. These are the 3 sensors behind the wheel. And then we have 7 or 8 that you see over here in front of the wheel. And these are negative because it's behind, and these are positive. The error bar shows you the coefficient variation, and you see that some of them are very low and some of them are high, depending on detectability. And what we want to do, we want to go from here to this curve that you see over here. So we want on y-axis damage. It can be IRI, rotting or cracking, and on x-axis either time or traffic. And essentially, we're just trying to define the survival curve from measurement at some point with some damage with the FWD or TSD, and get it. And of course, there's variability in the data, and there's variability in the site and equipment, and so we want to go probabilistic for this purpose. So we need an analysis algorithm to go to this from the raw data that I showed you, and there are a bunch of parameters to consider. You can make the model sophisticated, as we discussed before, having a tire interacting with the pavement and going at whatever speed you want. We have to consider the purpose of the analysis so that, get one of those 4-tier analysis. If you just only the network level, maybe the first level is good. Project level, maybe not. Quality of data is important, and that's why, till we figure out what's the variability of the site and what is the variability of the machine, probabilistic analysis is needed. And the 2 things that matters the most is to the end user, is just basically the timeliness of the response and the accuracy of prediction. Have that in mind, you are collecting 400 miles of data, 200 miles of data at 5 centimeter intervals. So there's a lot of data management. So what I would like to suggest, this is some of the thoughts that we had about this. And again, what I have damage over here and time or traffic on the x-axis. What we do, we just go and monitor the functional condition and basically try to predict what would be the survival curve when it would be terminal. And then there is, before that, there is an optimal. Or we can go and do solely structural. We can do TSD or FWD. And what I'm going to show you is with FWD because TSD is new. And of course, we have some variability in the result uncertainty. I just showed it with the arrows. So what do? We just go at some point, you remember, with TSD or the FWD, and when there is a certain amount of damage, and we're going to run and predict what would be the remaining life or terminal life or optimal life. And now we have to rely on this if they are separated. As you see, there is a separation between them. So what we were suggesting is a dynamic calibration of the responses. We always know at the beginning, let's assume that it was defect free, and then at the time that I'm running the test, I know how much is the damage. And I know this point, is there any way that we can combine the functional and the structural condition together to get a more accurate representative of the pavement? And that's, I show you an example over here. This is under the accelerated pavement testing, and what I have, the open symbols are basically the percent cracking of the site that we were testing under the accelerated pavement testing. And what you see, I'm just getting the FWD data at 20,000 repetition of the load. There is no damage over there. So if I want to do the functional, essentially this pavement would last forever. Looking at the trend and then try to forecast what's going to happen. If I do it based on the structural number that I get over here, what I would get, what would be the black line that you see over here, assuming that's going to be 0 at this point, and it's going to be some value that I accepted. But if I just go ahead and combine them together, so I have at least 1, 2, 3, 4, 5 measurement, and then consider that when I just try to do the prediction, you would see that I would get this black line. I'm sorry, we're going to get the green line that would predict that would be the damage that you're going to do. Now, if I go at 80, it's too late anyway, but we can do the same thing, 80,000. The rotting is a little bit better. We started rotting. Of course, rotting happens at the beginning faster, and that it's 20,000. You see that, if I just go only based on the structural, this is the prediction. If I go only on the damage, it's going to be this one. If you just basically do a dynamic calibration, combining all of them, this would be the curve that you're going to get. At the 80,000, the same thing. The green one is what you're going to get at that one. So it's more realistic. It's not perfect, but it's more realistic than doing one or the other. So it's been a long-winded discussion, so let me wrap it up. I just want to say that we have come a long way. We have improved a lot at least since 70-something that I started my civil engineering career. But still, there are a long way to go. Again, we have a problem that we don't know what we are building, and we don't know how much is the variability, and hopefully we can learn and improve our methods by combining the design, construction, and monitoring under the species of modulus, and remembering that the life cycle cost is important and not the construction cost. And to do that, we need to balance the 4 parameters that I have. Importance of the project, analytical model we use, field testing, and laboratory testing. Okay. With that, I would just have to thank a bunch of people, because this is 40 years of career, and that didn't happen in isolation. I just first want to thank my wife and my children putting up with me all these years, and letting me do what I'm doing. I want to thank my mentors, especially Ken Stokey. He taught me how to do good research and not just research. And then another guy, Lou Edgers, that was at Tufts when I was there, and he's the reason that I went and got a PhD. I still am grateful to him for his gentleness and being what he did. I want to thank the 135 graduate students we just counted, and those are the guys who did all this work, and I'm just talking about it. I have a lot of partners in projects, both we partners to do the projects, and then the partners that they funded us, especially TxDOT, National Road Research Alliance, NCHRP, and Federal Highway Administration. I have a map of the United States up over here, and whatever is colored is they either helped us, they funded us, or we have been there. So just before I retire, I have a few states to go. And most of all, it takes a village to do all these work. And these are the best village that you can hope for I lived in. And these are some of the people I want to thank, And Duran Yon I started in 88 at UTEP. He joined us in 89, and he retired in 2018. Mark Baker, inspiration, he's one of the most innovative people I know. We started since 1990, and I guess we're still working, even though he says that he's retired. Emad, 1996, now he's my boss, and it's a delight to work with him. Sergio Rocha, we could not do anything with him because he's the guy, he's an electrical engineer, and he's the guy who does all the instrumentation, and sorry, I lost it. Does all the instrumentation and all the good data that we get, and of course Cesar Triado is our modeler extraordinaire, and he's the youngest one, but we have been together 20 years. If you are lucky, all of us, we would have a group like this to work with. With that, I'm done, and I'll be glad to answer any questions if there's time.
Thank you so much, Professor Nazarian. That's a great talk, and I know it's a very complex subject. You did amazing things. Again, I just want to remind our audience to put their questions in the chat box. And as we get the questions, we'll ask Professor Nazarian those questions. I have a couple of them to start with. One of them you mentioned, one of your slides showed the empirical to mechanistic, pure mechanistic. And you mentioned pure mechanistic is still a dream. It's not there. We can understand all the variability of materials, layers, then loading systems, environments. So it's a very complex. So we're talking about large data of various layers, various types. So do you see that all these data-centric machine learning, you mentioned artificial neural network, will that be a one way of designing these future pavement systems? Because it's very difficult to come up with a complex simulation of all these variabilities in the layers.
Well, thank you for the question. This is a really good question. Well, what you say makes sense. The problem is that we need a balance between the model and the data. I dabbed a little bit in the nuclear power siting, and there were scientists involved that they were just wanted to look at the interaction of several parameters. And there was no way, the model was there, but there is no way to measure it. The same problem that we have, when we do the design, we just basically, somebody sitting in an office decides on a set of numbers to design the thicknesses, but we never see from then on if those numbers has been achieved, are they realistic or so that the model, what I like about the neural network, it can make it reasonably sophisticated, but then having the model, because of immediate response, you can go probabilistic very, very easily. So you can just not only just report a number, but report a range. And because of that, I also like that dynamic calibration that I did, so you can revise your thing. As you do monitoring, you can revise your survival curve, if you want to call it, and so on and so on. So it's a tool that, it can be good, or it can be realistic, or it can be unrealistic. But all it does is just, the way I see it, you can do it more realistic models with the parameters that you can measure, and then just do Monte Carlo simulation, do probabilistic analysis, so that, you have a more realistic picture.
My second question is related to intelligent compaction. I know that your works with MnDOT and NRRA. So what does it take for other states to implement this? Because one of the things you mentioned in your presentation, it covers the whole thing instead of spot testing at 2 or 3 points. What does it take to make it more routine use?
Okay, that's well, there was in the tens and so on and so forth, the technology was there, but the supporting technology wasn't there, like, the cloud data and things like that. So there are some setbacks. I think what I recommend, start slow. You don't have to go and just buy the Cadillac, just basically You can get a basic basic system and just something as simple as pass count. Make sure that the whole site is covered. You know that there are some we have some sites that if you see the guy who was running the roller just totally missed one lane. You know, never compacted it. But you know the density is on the other side and things like that. And you can do the uniformity is very simple and very easy. It's very real time. Do those, and if you are comfortable with that, then you can gradually improve it and then get the buyout of the contractors. But if you go at the beginning in the Cadillac, so you need a lot of resources and a lot of things, and that causes problem.
Thank you, Soheil. Soheil, I know you and me, you said we are like over the long term, but there are a lot of young people and young researchers and folks who are interested in this pavement area with the geotech focus. What is the next few things that really think, oh, this is where we're going to go in the next decade or next couple of decades? Where should they focus on?
You know that when you and I started, the pavement geotechnique was not very desirable or whatever, I don't know, was very sexy, right? You know, nobody said, hey, it's buried 15 feet into the ground, so who cares? And as I remember, we would go to the construction site. There are on the bridge. There are 6 inspectors looking at every single truck of concrete that is coming. But the guy who's building the embankment is putting like 3 feet of the 3-foot lifts, and you just draw a roller on it a couple of times, and because there was not even a requirement for density in that. So I think it's a really challenging area, and it is, you know, just basically coming up with models that, you know, we can design the foundation better and make it more durable. I think that's some area that needs to focus. The other one, again, we do not know what we are building. We don't have a database of how close we are between the design and the thing. So let's learn. And it's an exciting area now because people are paying attention to it.
The one final question I have is, this is something I was asked actually. So one thing during your distinguished career on this pavement engineering, there are times you may have thought, oh, this is something I missed at the time of initial phases of the work. I mean, this is a humbling experience for all of us. Do you have any such experiences? Okay, this is something I learned, lessons learned, like you just mentioned a couple of them. That is something I would like to know from you. Hey, this is something I really contributed, I learned from it, and this is where it's going to advance the understanding of the knowledge of pavement engineering.
Well, I always, if you are not doing something that, you know, you get humble, you know, you're not doing a real research, it's a consulting. It's a routine, a state of practice. It's not a state of the art if you do it. I think one of my, you know, since 81, I've been on the payroll of TxDOT. So I got my PhD paid by TxDOT, and then I started working research. And the very first project, it was very humbling because we came up with this really elegant and sophisticated system. And not considering the fact that, you know, you're impacting the whole industry, and, you know, essentially we were getting half of the quarries of the state out of the business, and a lot of the so especially I'm talking to the young faculty, you know, just because it's a very brilliant technical thing, it doesn't mean that it's practical. So just talk to the guys who are working in the construction and so on and so forth. I had, you know, he told me, hey, college boy, you're talking about billions of dollars. You know, that was the response I got, if that makes sense. So that's what I'm saying. Just don't, just because, you know, the differential equation is better than the previous differential equation, that doesn't mean that it's implementable. Just talk to people before you start making things more complicated. That's a lot of humbling things. And now I learned I don't do that, just a suggestion to people.
Great suggestion. I know how many times I was too academic in my thinking. So yeah, definitely that is something I learned from working in a team. Appreciate it. So I think again, a wonderful, great talk, and I think a very inspiring talk. And I'm going to request Brad to come and close the meeting. Brad, over to you.
Thanks, Anand, and great job moderating today. Soheil, fantastic lecture. And I just want to read back to you a couple of the comments that we got in the chat today. Carlos Fuentes says, great presentation, Dr. Nazarian. Your undergraduate class inspired me to pursue grad studies and a fruitful career in geotechnical engineering. Claudio Zapata says, Soheil, thanks for all your hard work and contributions to the transportation geotechnics field. And we got a million more thank yous in here. So I think one of the best things to me about award lectures, Anand, you did the Peck lecture a few years ago. And Soheil, now you're kind of in the club with all our award lecturers, right? Is that this is usually crowning achievement of an amazing career in the field. And your topic was fantastic for that today. A lot of times they're very, very specific. You really did a good job with that kind of overview while still picking out those areas that you see room for improvement from or that excite you. And so that's fantastic. So thank you for that and good job. And also thank you for putting the picture of the plaque in your title slide. So just so everyone knows, the Monismith Lecture does come with a handsome framed plaque that Soheil can now put up on his wall with his many other awards from over the years, and hopefully he's going to go get it. There we go. I think with the background, it's tough to see. Yeah. And if you hold it in front of you, you disappear. The magic of television, everybody. So you're going to have to invite everybody to come visit you so they can see it in person, Soheil. And they'll have to take our word for it. Yeah. And for all our viewers, thank you for being with us. If you liked what you saw, and I always say you're here at the end, so you probably did. So click like, subscribe, and get notifications. And you know what? The more you click like, the more this video shows up in people's search results. So when they're looking for pavement topics or geotechnical topics, you want this, or UTEP, you want this to show up so other people can see the lecture. But again, to all the viewers, thank you for being here today. And Soheil, thank you again. Congratulations from all of us at GI.
Thank you for the opportunity. I'm very humbled. Thank you very much. And thank you, Carlos. You made my day. And
Anand, great job moderating today. Well done. And our producer today was Amber Davis. We will be back with you in about 12 days with our next live stream. This is the end of Summer of Live, but it doesn't mean we're going to stop doing these events. On October 1st, join us for Boredom, which is a company. It's spelled B-O-R-E-D-M, as they talk about the future of geotechnical data and how we move on from boring logs. And October 2nd is, of course, the big one, Terzaghi Day. It marks the 9th year that we have celebrated Terzaghi Day at the Geo-Institute. We will have a live stream that day. Of course, all the other good stuff like the Terzaghi tree and the layered food and all of those things will appear. But you'll want to join us as Sebastian Lobo Guerrero is our special guest that day and presents on Terzaghi's work and legacy and how it's impacted his career. Whew, that was a lot. But we will see everybody very soon with more live events from the Geo-Institute. Thanks for watching today, everybody.